Well, hello and welcome to Skill Lesson 18, the segment and angle addition postulates. So I felt that there was some lacking information on the previous segment addition postulate skill lesson, so I thought we'd kind of dive a little deeper into it. It is a pretty basic postulate, so I think it wouldn't hurt for us to just take another look at it in a slightly different way. So just keep in mind, a postulate is a rule in geometry accepted as true without proof. I refer to it as common sense, not to make light of what it is, but for two smaller parts to create the whole. So that's really what we're looking at here. So, we can think of it in terms of a pizza. Two halves of a pizza make one whole. And in the same way, two line segments combined create a larger line segment. And when we look at the angle addition postulate, two adjacent angles, here's one angle and then here's another angle. These two angles combine to create this larger angle, which is the same concept with the pizza. So if we can understand how it works with a pizza, we can certainly apply it to segments and angles. So on this exercise, you'll actually notice that there's actually some work within the examples. I've created this skill lesson to be a little bit more unique. So you'll actually find some work within the examples, not necessarily just in the practice portion. So we're going to look here. I believe we are under, example B. Make sure there wasn't any missing in example A. So in example B, we're introduced to this word called midpoint, which you'll see the definition. It's a point that bisects a segment into two congruent segments. In other words, segments that have the same length. So let's take a look at one of our examples. It says, given M is the midpoint of RS, if RS is 10, then what's the length of SM? So I'm just going to draw a quick diagram. So M is the midpoint of RS, and they tell us that RS is 10. Well, if M being the midpoint divides RS into two congruent segments, we can divide this total length by 2 to find the length of RM and MS. 10 divided by 2 is 5. So the length from R to M is 5, and the length from N to S is 5. So SM is 5 units. Likewise, let's take a look at our next example. M is the midpoint of RS. We've already established that, so I'll just kind of draw that again. M is the midpoint of RS. And if RM is 12, notice there's a slight change in the information given. RM is 12, then MS is what, and RS is what? So we have two question marks here. So if M is the midpoint, then the distance from R to M has to be equal to the distance from M to S. Therefore, M to S is also 12 units. So we can throw that in here. And segment addition postulate tells us that these two units combined, or these two segments combined, create the total larger segment. So RM plus MS is RS, which is 24 units. 12 plus 12 is 24. Now, of course, we're taking a longer approach to look at something that seems basic because we're about to be introduced to some algebra here. And remember, all these expressions represent is things we don't know yet. And so we can't be too timid when dealing with algebra because it really just represents a number we don't know. So let's move forward on our practice here. So first practice, if Y is the midpoint of WZ, and you'll notice there's no diagram drawn, so my first encouragement is to draw a diagram. So Y is the midpoint of WZ. So that means that WY is congruent to YZ. So they tell us that the distance from Y to Z can be represented by X plus 3. Again, just some number we don't know. And the distance from WZ, so the total distance can be represented by 3x minus 4. It says determine the length of WZ. Well, the first thing we need to do is find what X equals in this equation, or in this example, so that we can plug in that value for X and find the length from WZ. Well, in this example, they tell us that the distance from y to z can be represented by x plus 3. Well, if they don't tell us anything, any expression that can represent wy, we can assume that it can be represented by the same expression as yz, so I'm going to put x plus 3. Because I know the distance from wy, that number has to be the same number from y to z. So if they don't give me an expression for wy, I can use the expression from y to z because it's supposed to ultimately be the same value. So we have all our missing parts because we know that wy, when combined with yz, we get the length of wz. So here's our formal equation. Now we're going to replace these segments with our algebraic expressions. So the distance from wy can be represented by x plus 3, yz, same thing, and wz, 3x minus 4. We'll combine like terms on the left side first. That is my encouragement here. Always simplify each side first, which oftentimes just means combining like terms. So we'll combine x and get 2x, 3 and 3 and get 6. Now we still have like terms, but they're on opposite sides of the equation. So now to combine these like terms, we have to do the opposite sign. So I like to move my smaller x to my larger. So to move a positive 2x across the equal sign, I'll subtract it. And of course, it'll cancel on the left, becoming 0. We'll be left with 6 on the left. 3x take away 2x is x, and bring down the minus 4. Last, to solve for x, this is x minus 4. So to combine that negative 4 with the positive 6, we have to add 4 to both sides. So x will equal 10. Now again, they didn't ask for what is x, but that was the first step in finding the length from wz. So now that we know x is 10, we should be able to go plug it back into this expression to solve for the length of wz. So wz is equal to 3 times, instead of x, we'll substitute 10. 3 times 10 minus 4. 3 times 10 is 30, and 30 minus 4, we get the length from w to z, which is 26. Now let's look at item 2, and we'll approach it the same way. Now on item 2, we have two different parts, a and b, but they're using the same given. So just keep in mind that the values will change from a to b, but we're going to use the same piece of given information. So m is the midpoint of Rs. So the first thing I'm going to do is draw a diagram. M is the midpoint of Rs, which means Rm is congruent to Ms. Definition of midpoint right there. So they tell us the distance from R to M is x plus 3, and the distance from M to S is 2x minus 1. And they want to know what is x equal and what's the distance from R to M. So if you notice, this one varies a little bit from item 1, because you might be asking yourself, well, I thought you said that from R to M and M to S, they have to be the same number. Notice that they gave us two different expressions. Please understand in math that two different expressions can represent the same number. In fact, think about what an equation is. For example, if I write x plus 3 equals 10, I'm saying that these two things, one an expression, one a number, they are the same thing. And clearly they look very different, right? X plus 3 looks way different than the number 10. But I am saying that this and the number 10 represent the same thing. And in fact, if we continue solving this, we see that x is 7. So 7 plus 3 is 10. So without algebra, hopefully you understand this. This is the same thing as that. So if we believe that the distance from R to M has to be equal or congruent to M to S, we're going to say that this expression has to be the same or equal to that expression. So we're going to make them equal to each other. So x plus 3 should equal 2x minus 1. These are two different expressions that if I put an equal sign between them, I'm showing that they are supposed to equal the same value. Just like 7 plus 3 has to equal 10. So we already have our equation based on the fact that M is the midpoint of RS. And really the equation we're using here is Rm is equal to Ms. So now let's solve for x. Again, I'm going to move my smaller x to my larger by subtracting it. I'll be left with 3 equals 2x take away x is 1x, but again, we don't have to write the 1 in front of the x, minus 1. Last but not least, to find out what x minus 1 equals 3, we add 1 to both sides, and x will equal 4. So that's the first step. They did, in fact, want us to find x, or what x equals. And now that we know what x equals, we can find the length of Rm by plugging in or substituting 4 for x. So Rm is equal to 4 plus 3, which is 7. So the length of Rm is 7 units. Now let's look at item B. Again, same diagram. M is the midpoint of RS. That means Rm is congruent to Ms, definition of midpoint. And let's see what they give us. Rm is equal to x plus 6, this expression. And Rs is equal to 5x plus 3. And they do want us to know the value for x and the length from S to M. So notice how even part B varies from part A. This goes back to what we did on item 1. When they do not give us an expression for the other half of our segment, we know that the distance from R to M has to be the same as M to S. That's what congruent means, same measure, or in this case, distance. So if I know this expression is going to ultimately be or become the distance from R to M, I know that the distance from M to S has to be the same thing. So I'm going to represent M to S with x plus 6. Now, the reason I do that here is because they gave us the distance from R to M and also the distance from R to S, the total. So they were giving us half of the distance. So we assume that the other half would be the same measure. And now we're going to show that these two halves combined create R to S. So the formal equation we're using is Rm plus Ms equals Rs. So we're going to replace Rm and Ms with the same expression, x plus 6, and Rs with the expression 5x plus 3. So even think of it here. We're saying that this right here equals this. Well, these are two completely different expressions, but we're saying that they are supposed to equal each other because of the second addition postulate, that these two parts combine to create the larger. So let me simplify this left-hand side, and we'll see it even more clearly like we did on A. X plus x will give us 2x. 6 plus 6 will give us 12, equal to 5x plus 3. Think about the equation we wrote on part A. We wrote this equation, x plus 3 equals 2x minus 1. These are two completely different expressions that we're saying should be equal to each other. Look what we just wrote here on item B. Two completely different expressions saying that they're supposed to be equal to each other. That is what an equation is. Oftentimes, two different sides that look completely different, but we're saying that they should be equal. So I'd like to combine bring my smaller x to my larger by subtracting 2x from 5x. So I'll do that. And we'll bring down the 12 equal to 5. Take away 2 is 3x plus 3. We will now that I move the x's to the right, I'll move my non-x's, my constants, to the left by subtracting 3. And I'll be left with 3x equals 9. And what times 3 is 9? That's essentially what this is saying here. And again, look, two different expressions that are supposed to equal the same thing. So we're going to divide both sides by 3 in case we don't know that, and we see 9 divided by 3 is 3. So they did want to know what x was, and now we need to find the length of SM. Which SM, they didn't really give us an expression for it from the beginning, but we did use the same expression from R to M, so we're going to substitute 3 for this x here. So MS is equal to 3 plus 6, and therefore MS is 9. So that is now looking at the segment addition postulate in terms of a midpoint, which the previous skill lesson did not address. Now we're going to turn our attention to the angle addition postulate. We're going to go and move into the practice here, the first practice for the angle addition postulate. So now we're looking at it in terms of angles, which an angle is when two rays join at a common endpoint called the vertex. So that's an angle. Two rays that join at a common endpoint called the vertex. So on item 1, when it says M is in the interior of angle RTD, first thing we need to establish is that when naming an angle, this middle letter has to be the vertex. That's how we name the angle. So we don't necessarily specifically know the size of the angle, or actually they do tell us the angle measures, but we're not going to draw it to scale. So please don't be thrown off for that. But they don't tell us that this is necessarily point R, this is necessarily point D, but this does have to be point T. And if M is in the interior, well, the interior of the angle is this space here. So M is somewhere inside of it, point M. So there has to be a ray from T to M. In other words, dividing RTD into smaller angles. So if the measure of angle RTM is 40 degrees, I'm just going to simply put that here. RTM is 40 degrees, clearly not to scale. And the measure of angle RTD is 65 degrees. So the larger angle, 65 degrees, we want to know the measure of MTD, this portion right here. Well, the formal equation is the measure of angle RTM, that portion, plus the measure of angle MTD. Those two smaller angles combined create the original angle we began with, angle RTD. So I'm going to replace our equation with known values. So RTM is 40 degrees. We don't know the measure of angle MTD. That's what we're looking for. And the measure of angle RTD is 65 degrees. So what plus 40 degrees is 65? Well, you probably did this math in your head, but again, we write these formal equations to show, especially when we get into algebra like we see on item 2. So we'll subtract 40 degrees from both sides to find the measure of angle MTD. And 65 minus 40 degrees is none other than 25 degrees. Now keep in mind all angles are, their measure is degrees. We're not dealing with centimeters or inches or anything, so always put that degree symbol after our value, especially if we're looking for a degree. Sometimes like on item 2, X is not in degrees. So now let's look at item 2. If H is in the interior of, I see I left out a little angle symbol there. So let's go and draw angle EFG. So we have an angle, again, or EFH, excuse me. They don't necessarily tell us that this point has to be E or this point has to be H, but this vertex has to be F. And they tell us that, or EFG, excuse me. I was right to begin with, EFG. H is in the interior. So somewhere floating out inside angle EFG is point H. So we'll just say it's right here. They tell us that the measure of angle EFH is 75 degrees. So let's show that. Clearly not to scale, but that's okay. The measure of angle HFG is 10x degrees. Again, just some number representing the measure from H of angle HFG. And the measure of angle EFG is represented by 20x minus 5. So EFG, our initial angle we started with, is 20x minus 5 degrees. So let's write our formal equation, especially now that we have a lot of algebra going on. So the measure of angle EFH, when combined with the measure of angle HFG, should give us the measure of the larger angle. These two angles combined create angle EFG. So let's replace each of these measurements with known values. So EFH we'll replace with the easy 75 degrees. HFG will replace with 10x degrees, and EFG will replace with 20x minus 5 degrees. Now, just so we're clear, we know we're eventually going to be solving for x on this equation. That's what we're doing. So we really, since all of these are in degrees, we don't actually have to show that they're in degrees. So if you just want to rewrite it as 75 plus 10x equals 20x minus 5, that's okay. Now let's combine like terms. We have to combine those across the equal sign. So I'm going to subtract 10x from both sides, and I'll be left with 75 equals 10x minus 5. And since I brought my x to the right, my x term, I'm going to bring my non-x term to the left by adding 5 to both sides. That'll give me 80 on the left and 10x on the right. Well, what times 10 is 80? Well, it's 8, but if you need to do that with a little algebra, we divide both sides by 10. 10 divided by 10 is 1 and 1x. And 80 divided by 10 is 8. So they did want us to find x first. So let's put in 8. And again, it's not degrees. X is the value that is simply helping us find our missing measure. So x equals 8. And they want us to find the measure HFG. So they tell us the expression that represents HFG, the measure of angle HFG. So measure of angle HFG is 10 times 8. And 10 times 8, we already looked at that a second ago, is 80. In this case, we are going to put degrees because we're talking about an angle measure. Now that's looking at a point on the interior of an angle. To take this idea of angle addition postulate a little bit further, now we're going to look at something called a bisector of an angle, or an angle bisector, which acts a lot like the midpoint, but when dealing with an angle. So we're going to pass through this example here and go and jump all the way to the practice. So given, and notice we have two different problems using the same given. They tell us that ray AH bisects angle MAT. So clearly I don't know the overall measure of, even though they do tell us MAT, I'm not drawing it to size. A is the vertex, T. But when they tell us that ray HX bisects the measure of angle MAT, then H, this point on the interior of angle MAT, has to be in a very specific location so that when this ray passes through H, the measure of angle MAH is congruent to the measure of angle HAT. That's what bisect means, so divided into two congruent parts. So ray AH is bisecting angle MAT into two congruent parts. So let's keep that in mind as we look at item A. So A says that the measure of angle MAT, so this larger angle here is 70 degrees, this larger angle MAT, then what's the measure of MAH? Well, if it bisected it, cut it in half. So what we're really looking for is half of our larger angle measure. Well, half of 70 degrees is 35 degrees. So the measure of angle MAH is 35. Now let's look at it in terms of our second information given. So I'm going to clear this out and redraw it just so there's no confusion. Still dealing with angle MAT and AH as an angle bisector. So again, these two angles have to be congruent no matter what measures they give us. So the measure of angle HAT is 80 degrees. So they tell us that HAT is 80 degrees, which I'm going to go ahead and tell you MAH also has to be 80 degrees. Not even looking further past the given information, it has to be 80 degrees. Now, obviously, this isn't drawn to scale. Neither of these angles are 80-degree angles. Think about it, 80 degrees is just shy of 90 degrees. So clearly not to scale. So please don't let that throw you off. So we want to know the measure of angle MAT. Well, these two angles, MAH and HAT, combined create the measure of MAT. So our formal equation is the measure of MAH combined with the measure of HAT is equal to the measure of MAT. So we know these two parts here, 80 degrees for both. So what is the measure of angle MAT? None other than 160 degrees. Again, just working on writing that formal equation, we're about to dive into the second part, which deals with algebra. So let's take a look. Again, one piece of given information, but two different problems. So ray FL bisects angle AFM. So I'm going to start with AFM. Notice all of my example angles are acute angles. I draw them the same way. That's not the part here we're looking at. We're just trying to create an equation to solve for our missing pieces. So ray FL bisects angle AFM. So L has to be in a very specific location such that the ray that passes through it cuts angle AFM into two congruent angles. So keep that in mind. So let's dive in. A says the measure of angle LFM is 11x plus 4. So LFM is represented by 11x plus 4. And AFL is represented by 12x minus 2. This is just like an example we saw with midpoint, where we know that the measure of angle AFL is supposed to be equal to the measure of angle, LFM. Yeah, the measure of angle AFL is supposed to be equal to the measure of LFM, but there's two different expressions. But again, these two different expressions should represent the same number. So we're going to set them equal to each other. So it's based on this idea that the measure of angle AFL has to equal the measure of angle LFM. So if we have two different expressions for these two angles, we have to set them equal to each other. So AFL is 12x minus 2, and it should equal LFM, angle LFM, 11x plus 4. So let's find the value of x that makes this side the same as this side. So I'll subtract my smaller x from my larger, and I'll be left with x minus 2 equals positive 4, and then add 2 to both sides so we can solve for x, and x will equal 6. Now, just to demonstrate my point, when we plug in 6 for x on this left side, 12 times 6 minus 2, and plug in 6 for this side, 11 times 6 plus 4. Well, 12 times 6 is 72. 11 times 6 is 66. 72 take away 2 is 70. And 66 plus 4 is 70. So that's what we're doing here. We're finding the value of x that really does make this expression equal this expression. So by plugging that in, we just found that the measure of angle AFL and LFM is 70 degrees. So x was 6. LFM is 70 degrees, and they want to know the measure of AFM, which is our original angle that was bisected. So these two angles, these two smaller angles, these two halves, if you will, were both 70 degrees. So 70 degrees plus 70 degrees is 140 degrees. Last but not least, item B. Again, same diagram. Again, we're going to draw L so that it at least looks like FL would bisect these two into two congruent angles. So the measure of angle AFM, this larger angle here, is represented by 6x minus 2. AFL, use a different color. AFL is represented by 4x minus 10. And they don't tell us anything about LFM, but we do know something about it. And so we're asked to find x and the measure of angle LFM. So here we see this example where we are given an expression to represent the measure of angle AFL. And if we're not given an expression to represent LFM, we can actually use that same expression because we know ultimately that the measure of angle AFL is supposed to equal LFM. So I'm going to go and show that this is also 4x minus 10. So these two halves right here, measure of angle AFL, when combined with the measure of angle LFM, these two halves should equal the measure of angle AFM. So using my diagram, I'm going to fill in my missing pieces. Measure of angle AFL, we'll write 4x minus 10. And likewise for angle LFM, 4x minus 10. And the measure of angle AFM is 6x minus 2. Again, we're writing that two different expressions equal the same thing. So don't get thrown off by that on the example we did for item A. So 4x and 4x will combine like terms, 8x, and negative 10 and negative 10 is negative 20. Again, I like to move my smaller x to my larger, so I'm going to bring this smaller x to my larger by subtracting it. We're combining like terms still, and to combine like terms, you only ever use addition or subtraction. So those still wondering what process I'm doing here, I'm combining like terms using addition or subtraction. In this case, I had to subtract 6x so that it becomes 0 on the right side, and it'll become 2x on the left. 2x minus 20 equals negative 2. Now to solve for x, again, we'll keep this x term on the left and add 20 to both sides, so that it becomes 0 on the left. We get 2x equals 18, because negative 2 plus 20 is 18. And then to solve for x, this is 2 times x, so to undo that multiplication, we divide, so that that cancels and becomes the number 1, so 1x equals 9. So x equals 9, and they want us to find, using x, the measure of angle LFM. So we use the expression 4x minus 10 to represent the measure of angle LFM. So the measure of angle LFM is equal to 4, substitute x with 9, minus 10. So 4 times 9 is 36. Take away 10, and the measure of angle LFM is 26 degrees. So that is the end of skill lesson 18, segment and angle addition postulates. Thank you for watching. Hope it helped.